Hi, I'm Samantha. Today I'm going to share with you my thoughts on the research of mine on the synthesis and characterization of palladium single atom catalysts for oxygen reduction reactions in fuel cells. Fuel cells offer a method of clean power generation by making use of earth abundant resources like hydrogen and oxygen. They directly convert chemical energy of the reaction into electricity and form water as the only byproduct. At the cathode, reactants undergo an oxygen reduction reaction or ORR, which is usually very slow and therefore needs a catalyst to improve the reaction kinetics. Methods like platinum and palladium are used as catalysts. However, since they are expensive and rare, we want to minimize their use and find material alternatives. A single atom catalyst is a type of catalyst in which individual atoms of a catalytically active element are dispersed on the surface of a support material such as metal oxides, which is cerium oxide in our study. This unique structure provides several advantages including increased catalytic activity, selectivity, and stability. Moving on to the introduction, the synthesis method is a two-phase solver-thermal process that involves oleic acid for synthesizing nanocubes and topo for truncated nanooctahedra. The study focuses on comparing the ORR characteristics of two different palladium-based single-atom catalysts supported on Cia nanocubes and truncated nanooctahedra. By comparing the ORR characteristics of the two palladium single-atom catalysts, the study can provide insights into the reaction kinetics and find the optimal catalytic activity. The chemical precursors used are shown. So going on to the synthesis. The synthesis, as I mentioned earlier, is basically a two-phase solvothermal process as represented in Figure 1. In order to synthesize nanocubes, we use a mixture of cerium, nitrate, hexahydrate, toluene, oleic acid, and third butylamine, which were then heated in a Teflon-lined stainless steel autoclave and at 180 degrees Celsius for 24 hours. Likewise, for synthesizing Cia truncated nanooctahedra, triple was used instead of oleic acid. The Cia nanocrystals were mounted on carbon with a loading of 40% by weight. Palladium was incorporated using palladium chloride precursors spotted by reduction using sodium borohydrate. Moving on to the results. X-ray diffraction or XRD reveals that Cia nanocrystals were formed since the characteristic diffraction peak observed in the XRD pattern matched with those in the standard ICDD card. We study the morphology of the crystals using transmission electron microscopy or TEM. As you can see on the left side, there are nanocubes of Cia which were synthesized using oleic acid, and on the right side you can see truncated nanooctahedra which were synthesized using topo. The catalytic activity of the palladium single atom catalyst was studied using linear speed potentiometry. As figure 4 shows, the ORR polarization curves of four different palladium loadings on Cia. As you can see, the catalyst with 0.38% by weight palladium loaded single atom catalyst showed the highest catalytic activity, indicating that this single atom catalyst has the potential to be an efficient electrocatalyst for ORR. Moving on to the conclusions and future works. From my study, we can conclude that palladium single atom catalyst can be synthesized using different morphologies of Cia support. The catalyst with 0.38% by weight palladium loading exhibited the highest catalytic activity for ORR reactions for fuel cells. And for future work, I think it would be interesting to investigate the ORR characteristics of the single atom catalyst with a wider range of palladium loading. And finally, we also want to characterize the single atom catalyst using energy dispersive X-ray diffraction or EDX to map the distribution of palladium on the substrate. So that was all I had to say here. Thank you for your attention and I welcome any questions you may have. Thanks.